Every time you ask an AI coding agent to reference a piece of web-based documentation, you are burning tokens on redundant infrastructure. Consider a standard 200-page documentation site. If an agent needs to access that data across multiple debugging sessions, it has to fetch, parse, and read the HTML repeatedly. You are paying for the machine to read the exact same boilerplate layout over and over again from scratch. Over a week of deep engineering work, that compounding token burn scales rapidly. A simple documentation query can end up costing dollars per prompt, making live web fetching a high-overhead method for heavy development tasks. This graph compares operational latency. Live network requests introduce highly erratic wait times, whereas local retrieval provides a perfectly flat, near-instant response. Furthermore, aggressive scraping triggers anti-bot protections. The agent gets trapped in a retry loop, and the session stalls entirely. The root of this failure is an architectural flaw. We are coupling the slow, messy process of data ingestion directly with the high-value phase of AI inference. By forcing the AI to act as a web scraper, we turn documentation retrieval into an unpredictable financial and operational liability. The alternative is to sever ingestion from inference entirely. We do this by preemptively processing the external web data into a clean, local storage layer. You cannot simply dump raw HTML text into a local folder and expect an agent to understand it. The files remain littered with menus, hidden script tags, and broken relative links. A true local substrate requires strict formatting. The data must be clean, the internal relationships between pages must be explicitly mapped, and the entire corpus must be easily indexable by a machine. Obsidian's architecture is built entirely on a local, linked markdown system. It provides a native environment for file-based relationships. By relying on double-bracketed Wikilinks, we establish a relational database that mimics the original website's navigation paths, but entirely without the HTTP overhead. The goal is to run the messy extraction process exactly once. After that initial pre-processing phase, every subsequent document retrieval costs you effectively nothing. Building a self-contained, offline Markdown wiki solves the latency problem and secures sustainable, zero-cost context loading for agentic coding. To automate this local wiki pattern, we use a Python CLI tool called Site-to-Vault. This chart maps the pipeline. Phase 1 executes a breadth-first crawl, using strict politeness controls to respect the host. Through content extraction, it isolates the main content. Phase 1.5 runs a cross-page de-boilerplate analysis across all fetched documents simultaneously. By measuring paragraph frequency across the entire site, it identifies and automatically strips out repetitive cruft, things like edit on GitHub footers or standard sidebar warnings. Removing this boilerplate before the agent ever sees the text drastically improves the signal-to-noise ratio. You save thousands of wasted tokens per query simply by dropping the repeated footers. In phases 2 and 3, the clean text is converted to Markdown, and every internal web URL is dynamically rewritten into a local Obsidian wiki link. This rewriting ensures that when an AI agent decides to follow a reference to another page, it accesses the local file instantly, rather than triggering a dead-end external web call. But even with perfectly clean Markdown, feeding a massive full-page file into an LLM's context window is inefficient if it only needs one specific paragraph. To achieve precision extraction, the pipeline calculates byte offsets. This timeline illustrates Phase 4. The tool scans the final Markdown document, computing the exact byte start and stop points for every heading. With these coordinates, an agent can surgically extract only the required subsection, dropping the surrounding text entirely. Byte offsets transform a static folder of text into a highly precise, searchable database, keeping token usage as lean as possible during inference. Phase 5 organizes the vault by generating root and folder-level maps of content. These act as high-level hierarchical indexes. Finally, Phase 6 compiles the central index, manifest.json. This file contains the metadata for the entire corpus. The manifest is the definitive map for the AI. It lists every note, every single heading, every internal link, and every byte offset in a single, lightweight package. By reading this single JSON file first, the agent instantly understands the structure of the entire documentation site. It never has to execute costly, time-consuming file system traversals. To put this architecture to work, users have two deployment options. The standalone Python CLI is designed for engineers who want to embed the tool into existing scripts or orchestrate tasks exclusively through the terminal. For a visual approach, the Obsidian Site-to-Vault plugin integrates directly into Obsidian. It wraps the binary in a GUI modal and exposes all the CLI flags in a Settings tab, streaming live progress into a crawl log view right in the sidebar. Site-to-Vault delivers the strict, machine-readable indexing that AI agents require, paired with the interface flexibility that engineers expect. To see this in practice, imagine an agent tasked with deeply comparing API structures across Claude, Codex, and Gemini simultaneously. First, you use the tool to crawl all three sites, depositing them into a single local vault structured with isolated namespaces, docs Claude, docs Codex, and docs Gemini. You then instruct your CLI agent to evaluate how all three platforms handle a specific function, like function calling. This diagram shows the optimized path. The agent reads the single manifest.json file. Because all the metadata is there, it instantly locates the exact points of comparison buried inside the three platforms. It skips the file tree entirely. It extracts only those specific byte offset sections from the relevant markdown files, ignoring hundreds of pages of irrelevant data. The agent completes a highly complex multi-platform documentation analysis in seconds, and your token bill for the data retrieval remains flat. By utilizing a multi-namespace vault, you transform a high-latency scraping operation into an instant, free local query. To maintain high-velocity context, developers are increasingly shifting the ingestion phase out of the real-time inference loop. Using advanced, expensive reasoning models to perform redundant text extraction on static web documentation is an inefficient use of compute. This cumulative line chart illustrates the economic reality. When querying static knowledge domains, local preprocessing mathematically defeats dynamic web retrieval over time. The practice of using high-level agents for raw, redundant data ingestion is a high-friction approach that can be avoided through preemptive substrate preparation. When AI implementation is cheap, the true scarce resource is context. Curating a self-built, machine-readable local wiki is the most precise and valuable asset an AI engineer can maintain.